Hello everyone, welcome to another hands-on session. In this video, we're going to start coding 2D FEM. And in this video specifically, we're going to discuss the discretization of a uniform mesh. So what I mean by a uniform mesh is exactly like this. So unlike the previous videos where we, discussed the truss structures, we now have this, square-like mesh, let's say a rectangle, and then we're going to divide this mesh into pieces, which are elements. And then we're trying to determine the nodes and the elements, positions, depending on these parameters. So we have four parameters here, which are d1, which is the length of the mesh in the x-axis. D2 is the length of the mesh on the y-axis. P and M determines the number of pieces that we want to divide this length into. So let's say if M is 3, then this portion will have 3 pieces. So 1, 2, 3. And then we're going to have 4 nodes. So that's the logic behind it. In the upcoming videos, we're also going to discuss a mesh which has a circular void in the middle and then has the same parameters as the uniform mesh. But this one's also going to have a R parameter which defines the diameter of the circular void. But that's for another video. So let's start with the element types. So we're going to discuss these two element types in this video. We have D2QU4N, which is a 4-noded quadrilateral element. And we also have a D2TR3N, which is the 3-noded version of a triangular element. Although we're going to discuss only these two elements in this video, the other remaining 3 elements, which are 8 and 9 noded version of this one and 6 noded version of this one, can be derived from these two elements. So you can do that on your own. It's pretty straightforward, but in this video, I'm just going to discuss these two. So that's it. Now, what are we trying to get initially? So let's run the script that I wrote previously to show you what we're trying to find. So we have the element list and we also have the node list. So let's take a look at this figure. So as you can see, we have the nodes on every single point and then we have the numbers on them. So this is node number 1, node number 2, 3, 4, 5, and then 6, 7, 8, 9, 10, 11, 12, and so on and so forth, up to 20. We also have the element numbers, which are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so let's take a look at the element list. So as you can see, element 1, which is this one, has the nodes 1, 2, 7, 6. So 1, 2, 7, 6. It has to be counterclockwise for every single element. Don't forget about that. The order matters in this case. And if you look at the second element, we have 2, 3, 8, and 7. 2, 3, 8, and 7. So they all start from the bottom left corner and then move counterclockwise. So we're trying to get this in this session. If you also look at the node list, you can see the coordinates of the nodes. So let's say the first node, which is in the 0th index, but node number 1, it has the 0, 0 coordinates as x and y values. And if you look at the second one, we have 0.25, which is this point on the x-axis, and then we have 0 as the y coordinate. But of course, we can't just define every single node on our hands. So that's why we're using parameters such as P, M, D1, and D2. So that's what we're trying to get. Now, let's start with defining defining the dimensions and numbers of the parameters. So I will define D1 as 1, D2 as 1, P as 4, M as 3, and then the element type is D2QU4N, which is this one. So as you can see from the figure, it's a quadrilateral element throughout the whole mesh. So that's it. And then I'm going to define a function, uniform mesh, which takes these parameters that I defined above. And then this function will return NL and EL as the result. So that's what we're trying to do in this session. Now, let's define the function, but first let's start with importing NumPy, as always. So let's define the function def uniform mesh, which takes D1, D2, P, M, and element type as the parameters. Now, in this case, the problem dimension is 2, because we only have x and y axis. But if you'd like to work in three dimensions, then you can set this to 3. But in this case, it's 2. So what I'm going to do first is to define the coordinates of these 4 points at the corners. So this will be 0, 0, this will be 1, 0, 1, 1, and then 0, 1. So let's call this Q, and then let's create the NumPy array as, so we'll have 4 coordinates, so I'm creating 4 brackets, just like this. So the first one's going to be 0, 0, as I've said before. The second one is going to be D1 and 0, because we picked D1 as 1, and then this length is D1, so this portion, this point's coordinate will be D1 to 0. And then I'm going to define this coordinate right here, which is going to be D0 to D2, this coordinate. And then finally, this point's coordinate is going to be D1 to D2. So this is for corners. Now, let's also define the number of nodes. So if I have P pieces in here and then M pieces here, then I'm going to have P plus 1 nodes here and then M plus 1 nodes here. So the number of nodes will be P plus 1 times M plus 1. So it will give me the whole number of nodes. So P plus 1 times M plus 1. Let's also define the number of elements. So if we have P pieces right here and then M pieces right here, again, according to the same logic, if we multiply these two numbers, we're going to get the number of elements for the entire mesh. So it's going to be P times M. And then since we're working for D2QU4N, the nodes per element will be 4. But if we were to work on D2TR3N, nodes per element will be 3. But in this case, initially it will be 4. So let's say 4. Now, let's start with the nodes. Just like in the trust structures, the FEM for trust structures, we're going to start by creating a NumPy array, which is full of zeros, and then the size of it will be number of nodes times problem dimension, as we've discussed before, because for every single node, I'm going to have x and y coordinates. Now, so we have to define the increment in the horizontal direction and the vertical direction. So, so that I can, define the nodes by adding this increment over and over again. So, we have the coordinates defined here. So let's define the increments in the horizontal direction. All right, what we have to do here is find the length here and then divide it into p pieces, because this edge is divided into p pieces here. So let's say Q10, which is the first row of this, and then the first column, this coordinate right here, minus Q00, which is, this is the second row and the 0 column, so D1 minus 0. So this one represents D1, and this one represents this 0 here. And then once we find the length, we have to divide this by p, because that's how many pieces we have along the horizontal direction. So this is going to be the increment in the horizontal direction. And then in a similar manner, we're going to get the vertical increment, so 2 to 1. So second row or third row, and then second column. So D2 minus Q01, which is this guy. So I'm subtracting 0 from D2. And then we're going to divide this by m, because in the vertical direction, we have m pieces. And then that's going to give me the increment along the vertical direction. So increment in the vertical direction. So that's it. Now, I'm going to define a for loop to go through the x-axis and y-axis, and then place nodes using the information that we have right here. So I'm going to start by defining an n number to be used in the for loop, and then this will allow me to go through the rows in the node list. So for the first node, second node, third node, and so on and so forth. So this will allow us to go through rows in NL. Now, I'm going to define a for loop for I in range, starting from 1 to n plus 2. So the reason for this is because we're going to have n plus 1 nodes in the vertical direction. If we have n pieces, we're going to have n plus 1 nodes here, and then this is going to go through, start from 1, 2, 3, 4, and then end at n plus 1. So that's why we type this. And then similarly, we're going to have a for loop for the horizontal direction. So for j in range 1 to p plus 2. So it's the same logic as in here. We have p plus 1 nodes here, so it's going to go from 1 to p plus 1. So that's it. Now, I'm going to define, so what I'm trying to do here is place the x values of the nodes in the whole mesh. So in the node list, it's going to be the nth node, which is going to be 0 initially. So it's going to be the first node, second node, third node, and so on and so forth. So nth node, and then the x coordinate for the nth node, which is the first column. And then this is going to be equal to q0, 0 plus j minus 1 times a. So essentially, we're picking the very bottom left side of the whole mesh, which is this point. And then we're adding the increment times the number of times the increment. So initially j is 1, so we're not going to add anything. So the first coordinate of the first node will be 0, 0. And then let's say j is 2. If j is 2, we're going to add 1 times a, the increment. So it's going to be node number 2. And then it's going to be node number 3, 4, 5, so on and so forth. So that's the logic behind it. So similarly, let's define the y coordinates. So this is going to be 1 this time, which is the y coordinate of this node. And then this time, this is going to be I, because we're trying to add the increment horizontally. So once we're done with the first row, we're going to move on to the second and third row, and etc. So that's the whole logic behind it. And then this time, we're going to add the b increment, because that's the increment in the vertical direction. So this is for x values, and this is for y values. And then finally, to switch between the nodes, I'm going to add 1 to n each time I complete a loop. So it's going to be node number 0, 1, 2, 3, 4, until 20 in this case. So that's it. Let's move on to the elements. Just like previously, I'm going to create an empty array full of zeros. So this is going to be number of elements times nodes per element, as we discussed before. And then again, just like in here, I'm going to define 2 for loops. But this time, this is going to go from 1 to n plus 1, and this is going to go from 1 to p plus 1, because we have n pieces here and p pieces here. So, so this starts from 1 and ends at m, and then this starts from 1 and ends at p. So let's first define the elements in the first row. So 1, 5, and 9. Element number 1, 5, and 9. And then we're going to determine the rest of the elements depending on the node numbers of these 3 elements. So for the case if j is equal to 1, so let me write the expression first, and then I'm going to explain why it's that way. Times p plus j minus 1, first column, and then this is going to be I minus 1 times P plus 1 plus J. So now this is going to be the first column of the element list, and then this is going to be equal to 1 in this case, node number 1. So why is that the case? We're trying to determine the very first node of the whole mesh. So if I is 1, this is going to be 0, and then j is going to be 1, and then this whole thing is going to be 0, and then the first element, the first number in the element list will be equal to the same thing we wrote here, but without the index, without the minus 1 for the index, but also it's going to be p plus 1. So why are we multiplying this p with this expression? So we have p elements on this edge, and then once we're done with this row, it's going to go to the second row. So let's say I is 2 this time. So it's going to be p plus j minus 1, which is p. So p is in this case 4 in this example. So 1, 2, 3, 4. And then it's going to be the fifth column of the element list. So that's correct. So it's going to be this node. So the same idea is here for the elements. So I want to add p to this number to get to the second row of the element list. So it's going to be 1, so first element, fifth element, and ninth element. This minus 1 right here is to correct the index of the NumPy array, because as we've discussed before, indices start from 0 instead of 1 in Python. So that's why we put the minus 1 in here, but we didn't put the minus 1 in here because we're not looking for the index, but we're looking for the number itself. So in this case, it's going to be 1. 1, 6, and 11 in this case. So once we've done that, the rest is pretty straightforward if you got this. This is the most difficult part of this algorithm. So now what we're going to do here is I'm going to copy this. And then this time we're looking for this node, okay? So this node will always be 1 more than the first node. So if I add 1 to the previous node, I will get the second node of the element. So in this case, it's if I add 1 to 1, it's going to be 2. If I add 1 to 6, it's going to be 7. And if I add 1 to 11, it's going to be 12. So all we have to do here is take this expression here and then add 1 to it. So that's it. Now, for the third and the fourth node, let's start with the fourth node here. So I will have to add p plus 1 to the first node. So we have p plus 1 nodes here, and then if I add p plus 1 to this node, then I'm going to come to the node number 6 in this case here. So that's why we add p plus 1 to the first node here. And then finally, for the third node, which is this one, or this one, or this one, if you add, so we're going to have to copy this, and if we add 1 to this, so let's say if I add 1 to 6, it's going to be 7, 12, and then 17, I'm going to get the third node, depending on the fourth node of the element. So that's it. If you got the logic here, the rest is pretty straightforward. So in this section, we're trying to determine the rest of the elements and nodes in here. So far, we've only done these 3 elements in this case, the first column of the elements. So I'm just going to copy these. And then, so let's delete these 2. And then I'm going to start with the fourth node of the element. So for this element, it's going to be 16, or for this, it's going to be 17, 18, 19, and so on. So I'm also going to delete these 2 here, and then I'm going to explain why. Now, the second node of the previous element will be equal to the first node of the second element. And then the fourth node of the second element will be equal to the third node of the first element. So that's what we're trying to get here. Now, I'm going to copy this and paste it here, but this time I'm going to change this to -2. So essentially, I'm getting the previous element instead of the current element. The current element is represented by this expression. So if I subtract 1, I'm going to the previous element. And then the previous element's second node, in this case 2, when I is 1, the previous element's second node will be equal to the first node of the second element. So that's why we're doing this. And then I'm going to copy this. And then let's make this 2. So let's look at the fourth node of the current element, which is this one. So this is going to be equal to the third node of the previous element. So that's why we put 2 here. So once these 2 are done, we can just copy these 2. And then let's define the rest of the nodes. So 1, 2, and then all I need to do is this. So let me explain it. The second node of the current element, which is this one, will be equal to 1 plus the current element's first node. So we will also have to change this to 1. So essentially, I'm adding 1 to this, 1 to this, this, and this, so on and so forth. And for the last one, for the third node of the elements, according to the same logic, I have to add 1 to the fourth node of the current element. So add 1 to 7 is going to be 8, 13, and 18. So that's what we're doing here. So the ordering is done. We're done with the element list. So let's save this to the desktop. And let's call this uniform mesh. Now, as you remember from the beginning, we defined the dimensions and parameters for the mesh. We also defined the element type. And then now we're going to call the function here. Now, I've already written this portion right here because it's all about plotting. But let me explain shortly. So I define a number of nodes at the size of the node list vertically. So the number of nodes will give me the number of rows will give me the number of nodes, and then the number of rows in the element list will give me the number of elements. And then I created a figure, a matplotlib figure, as you can see here. And then you can just copy these for loops to create this plot. So essentially, this annotates node numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then if the element type is D2QU4N, I'm going to annotate the element numbers, which are the numbers you see in the middle. So 1, 2, 3, 4, 5, 6, 7, 8, the blue ones. And then you determine the 4 lines to plot here. So x0, y0 is, for this case here, this, and this. And then you connect these nodes with the plot function. So let me just show this completely so you can do that. So you can just take these lines and then copy to plot it. So if you do this, so let's just organize this. Okay, everything's fine. So if you do this, now you can see that we have the same plot as in the picture. And then the element list and a node list is the same as we discussed. So if you change the values here, of course the plot's going to change. So this is where P and M are both 4. And then you can play with this as you want. So that's it for the quadrilateral element. Now we're also going to discuss the triangular element, the 3-noded version. So in this code, you have to add a section, add an if block here. So let's say if element type is equal to D2TR3N. So the logic behind creating triangular elements is that, so initially we have the quadrilateral elements right here, and then we're going to convert this to the triangular elements. So essentially I'm dividing every element into 2 pieces to create triangles, and then I'm assigning the node numbers and then the element numbers for each newly created element. So that's what we're doing here. So the new node per element will be 3 because it's 3-noded, so it's going to be 3. And then the new number of elements is going to be 2 times number of elements for the previous case. So it's going to be multiplied by 2 since we're dividing everything by every quadrilateral element to 2 pieces. So we have to multiply this by 2. And then the new element list will be in the size of these 2 parameters that we just defined. All right. So let me just leave some notes here so you can understand. So this is for triangular element, and every element will be divided into 2 triangles, and then this is going to be the new size for the element list. Now we're gonna put the values into this new element list using the previous element list that we defined for the D2QU4N. So for I in range, from 1 to number of elements plus 1. So this will go through, like, start from 1, 2, 3, 4, and then go to number of elements. Now, let's just do this, and then I'm going to explain why. I minus 1, 0 is equal to EL I minus 1, 0. So, so the first node number, so the first element is this one. Let's say the first triangle is going to be the triangle at the right side. So the nodes of this triangle will be 1, 2, 7. So which means that the first node of the previous 4-noded element will be the first node of this triangle. And then the second node of the previous one will be also the second node of this triangle. And then the third node of the previous element will be the third node as a triangular element. So that's why we did this. So the first node of this triangle will be equal to the first node of the previous quadrilateral element. So I'm just going to copy this for the next node numbers. So it's going to be 1, 2. And this is going to complete for the first triangular element. Now, let's just copy this. And this is going to be for the second triangular element. Now, the first node of this second triangular element will be the first node of the previous quadrilateral element. So the first line is going to stay the same. The second node of this triangle will be equal to the third node of the previous element. So this has to be 2. And then finally, the third node of this triangular element will be equal to the fourth node of the previous element. So it's going to be 3. So in this for loop, this is going to complete the whole element list. And then finally, I'm going to replace the original element list with this new list that we just created. And then to use this in plotting, I have to convert this to integers. So as type int, and then return the NL and EL. So that completes the uniform mesh. Now, if you put D2TR3N as the element type, now this time in plotting, you have to change a few things. First, you need to divide this by 3 instead of 4 in here, because we have 3 nodes. And then you will have 3 coordinates instead of 4 coordinates. And then the rest is pretty much the same. So if you run this, now you can see that the elements are divided into 2 pieces for each element. So initially this was element 1, the whole thing, and then this is divided to 1 and 2, 3, 4, 5, 6, 7, 8, so on and so forth. So that's how you create a uniform mesh in Python using 2D FEM. I hope you guys enjoyed. I will see you guys in the next video. You can ask me questions if you didn't get anything by email, and I will try to help you as much as I can. Take care.